Hello everyone, hope you guys are doing well. So we would be continuing our journey, and we were we already completed um the physical layer. So today we would be starting with the data link layer. Now this layer will come just after the physical layer. Okay, so the goal or the objective of the data link layer, so let's split let's have individual, right? This is, so one is for data. So data basically is the information. So this is data. Now what is this link? Okay, so this, remember, just after this layer we have the physical layer, right? So this layer will perform linking. That is, so in the physical layer you only have analog signals, right? So this will do basically converting the ones and zeros to a physical electrical signal, which will be transmitted using the physical layer. So this is that linking that is going to happen. Okay, so the first topic that we would be discussing today is error detection. And let us understand. Now, networks must be able to transfer data from one device to another with acceptable accuracy for most applications. Now this is basically another device that works, and the data link the device that works at data link layer is the modem or the gateway. So remember the modem that we get from the ISP. So why it is a modem? Because it has demodulator and modulator. So if you see a network, so this is the entry point to our local network. So this is from ISP. This is from ISP coming to our modem. So this is ISP, and this is the modem, and then we have local devices connected to this modem, right? You have devices connected to the modem. So this is the entry point of our network from the ISP. So here at this point we will be having electrical, and then here once we enter the modem, this is going to get converted to bits. So we need to make sure that the bits that there is, first of all, what can happen is the signals coming here may appear that it is a 1, but then they actually may be a 0. So then again that is the problem. This is on the center side. Like if we are the sender, right? We are going to go from the data link to the physical. Suppose if we are on the receiver end, then again we need to convert the electrical into proper bits, right? Sometimes what may happen is we may assume that something might be a 1, but then it might be a 0. So then we need to do something called as error correction. Now error detection, and hence we need to do this error correction and detection. Okay. The networks must be able to transfer data from one device to another with acceptable accuracy. For most application system must guarantee that the data received is identical to the data transmitted. At any time data transmitted from one node to the next, they can become corrected in a passage. So many problem can occur, right? So then we need to make sure that at any given point we are always transmitting what we wanted to send, right? Suppose this is two nodes. Um, suppose so data can be lost, right? It's physically going to go here. So sometimes um, because of the medium issues or anything else, but we need to make sure even if there is some error or noise which is corrupting the data, still the data here should be received with the utmost accuracy. So what happens is when this is going to be signals, right? So then and this is going to be a modem 1 and this is our modem 2. So then what happens is whenever there is problem or noise in the channel, extra bits are introduced. We need to make we need to ensure that we receive only what we transmit. No extra bits are added. So because of these extra bits at M1, I'll have to perform more error correction, which is going to hamper my speed. Hence, whenever your speed reduces or is there anything, um, the the most common cause is when you look at the modem. So every modem gives the error statistics, right? So it's at that time you will see that the percentage of correctables, that is basically how much correction is being done, is more. Now, introduction. Now, types of errors. Whenever bit flows from one point to the another, they are subjected to unpredictable changes because of interference. Now, these interference can change the shape of the signal. Now, so let's. This is RF signal. That's what I needed. Okay. Now let's go. Now see types of errors. So first is single bit error. What we say that one single bit has changed. Then we have multiple bits. Now whenever bits fill up, the interference can change the shape of the signal. In a single bit error, a 0 is changed to a 1 or a 1 becomes a 0. So I can say this is 1 becomes 0 or vice versa. This is a single bit. The term single bit means that only one bit of a given data unit, such as a byte, is changed from 0 to 1. And then the figure shows the effect of a single ping on a data unit. To understand the impact of change, imagine the group of 8 bits are being sent, right? Um, Single bit errors are least likely to cause error in serial data transmission. To understand why, imagine data sent at 1 Mbps. This means that each bit lasts only 1 by 1 microseconds. For a single bit error to occur, the noise must have a duration of 1 microsecond, which is very rare, but normally lasts much longer than. Now, burst error. The term burst, then the other type of error that we have is burst error. As the name is suggests, so we'll have more than one bits. One or more than one bit. This is nothing but we call as burst error. Okay. Now the figure shows the effect of a burst error on a data unit. In this case, so more than one bits are going to change. The burst error is most likely to occur than a single bit error. So what he's saying, the probability of this occurring is less because bits will last only for a very short period of time, and for that the noise level should be such, it should also be very small. It's very difficult to achieve that. However, burst error can occur. Redundancy. Now what is redundancy? The concept of detecting errors is called as redundancy. To be able to detect correct errors, we need to add. So now what is the solution? So what we do is, since multiple bits which, so how to eliminate these errors? Now one method will be is to add or to pad or to do bit stuffing. You add more bits at the start and at the end. So first method is you do something called as adding bits. Okay, now these redundant bits are added by the sender and will be removed by the receiver. This presence, so the presence allows the receiver to detect or correct the corrupted bits. Okay, now detection versus correction. Now correction is more difficult than detection. In error detection, we are just going to predict how much error occur, if you are going to see how much error has occurred. However, when we talk about correction, we are going to correct it. Like if a wrong bit was sent, then we need to send the correct one. The number of errors and the size of the message are important factors. If we need to correct one single error in an 8-bit data, we need to consider 8 possible locations. So if we had to correct 2 errors, then we need to consider 28 possibilities. You can imagine the receiver's difficulty in finding 10 errors in a data of 1000 bits. So depending upon how many data bits are sent, corresponding number of errors will occur. A forward error recursion versus retransmission. Now there is so now once what we said is detect. So detection is to detect if error has occurred or not, and correction is when we are going to correct the bits. Okay, now forward error correction versus retransmission. Now there are two main methods of error correction. First, either you do forward error correction. In this process, the receiver tries to guess, so you kind of do bit stuffing, and then based on those redundant bits, it will check what the actual data is. This is possible, as we see later, if the number of error is small. The correction by retransmission is a technique where the receiver detects the occurrence of an error and asks the sender to send the bits again. So for correction, there are two methods. So one is you do retransmission or you do bit stuffing. You do bit stuffing or add redundant bits. Okay, now uh, 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 correction by retransmission is basically what sending the message again, right? Now, redundancy is achieved through a variety of coding schemes. The senders as redundant bits through a process that creates a relationship between the redundant bits and the actual data bits. The receiver checks the relationships and then detects or corrects the errors. The ratio of redundant bits to the data bits and robustness of the process is shown in the coding scheme. Okay, so then you have a message, then you have a generator. Okay, so how it will look now? What are different types of modulo arithmetic? Now, before we there's something called as modulo and system. Okay, so when we say um so modulo to arithmetic. Now this arithmetic, the modulus n is 2. We can use only 0 and 1. Operations in this arithmetic are very simple. The following shows how we can add or subtract 2 bits. Notice particularly that addition and subtraction give the same results in arithmetic. Okay, we use XOR operation for both addition and subtraction. Okay, now blocking code. Now in block code, we divide our message into blocks, each of k bits. This is called as data. Now, so what we are studying is different types of um so then how to check for how to perform this now we are checking is redundancy. So the first method is that we do is we call as block coding. And there are different ways in which you can do block code also, right? There is linear block codes, there is cyclic codes, then there is also checksum. So these are all basically different methods how bit stuffing can occur. Let's so let's say techniques for bit redundancy. You do parity bits. It's a very old method, and then you have Hamming code. Then you have different types of code to check the main goal is how we are going to do how we are going to check whether an error occurred. So now this is done using codes, right? We'll be converting, and there are different types of methods which can be done. Even there is convolutional codes as well. So block codes, as I said, again there are different types. But this is BCH. There are a lot. So the whole goal is here we are going to check whether a redundancies occurs. So redundancy is basically where we are going to do whether a 1 was transmitted and a 0 was received, or a 0 was transmitted and a 1 is received. Now let's come to data link. The two main functions on the data link are first is data control and media access control. The first data link control deals with design and process of a communication between two adjacent nodes, node to node communication. We discussed this in this chapter. The second function of data link is media access. The data control function includes framing, flow, and error control, and software implemented protocols that provide smooth transmission of frames. Now the first thing we discuss framing. So we'll be studying what framing is, and then we will be dealing with media access control and the data link control of framing. Now, data transmission in the physical means bits in the form of signal from source to destination. The physical layer provides base synchronization to ensure that the sender and receiver use the same bit durations and timings. Data link layer, on the other hand, needs to pack bits into frames so that each frame is distinguishable from other. A postal system practices type of framing. This simple act of inserting letters into an envelope separates one piece of information from another, so the envelope serves as the delimiter. In addition, each envelope defines the sender. Okay, so then now what we do is we do something called as framing of. So remember, whenever we are going to send the data, we are not going to send it bit by bit, because then at the so let's see why we do framing. Like, what's the advantage? Yeah, so as I said, if we just send the bits, then we will, at the receiver side, we don't know whether is this the actual data or is it the error. So what we do is we do something called as frames. Instead of single bits, we we send frame of bits. That means we do like we don't send a single, we will send it in the form of frames. Now framing can be done in two ways. First is you have a fixed size frame. So remember what all protocol you use at the receiver side, same will be present at the sender side. So you cannot say that you're using fixed size framing at the sender and then you're using variable size. This will not work. But however, the frame sizes made, same thing will be at the receiver end. Now you might say, where is this things at the receiver end? Now this is something that occurs at the block at the modem level, right? So then the modem manufacturers will take care of this. Okay. So then what? Okay, now in a character oriented protocol, data, a main discussion in this chapter is the frames can be fixed or variable. In fixed size, there is no need for defining. But so now there is something. We know if the size is fixed, we don't need to check like when a new frame arrives, because the size is fixed, right? But then the problem in this is it will lead to data redundancy. So we do not uh, we try not to use uh, we will try not to use fixed size frames. So hence we do something called as variable size. Now the problem is variable size. We don't know when a new frame is going to come. Let's uh, let's we don't know when the new frame will arrive, so then we need to have some kind of mechanism that checks when is the new frame going to arrive. For this process we do something called we will see some method. Now in variable size frame we need to define the end of the frame and the beginning. So historically there are two things we use here. So again for this, so then again there is something called as bit stuffing. And then this is bits, and then this is byte. Okay, now to process a character. So okay, we don't call this, let's say, so the two approaches that we use is character, and then the other one that we say is bit oriented approach. Okay, okay, now a character now okay, a character oriented data are in a character oriented protocol. Data to be carried are 8-bit characters from a coding system ASCII. The header, which normally carries the source and destination address and other control information, and the trailer, which carries error detection or other correct redundant bits, are also multiples of 8 bits. To separate one from an 8-bit flag is added at the beginning and at the end of the frame. The flag, composed of protocol dependent characters, signals the start or end. Now the figure shows the frame. So first you have 8 bits, that is a byte, and then again at the end. Okay, now character enter was only popular when only text was exchanged by the data link layers. The flag could be set to any character for text communication. Now, however, we send other types of information such as graphs, audio, and video. Any pattern used for flag. If this happens, the receiver, when it counters this pattern in the middle data, thinks it has reached the end of the frame. To fix this problem, a byte stuffing strategy was added to character oriented framing. Now, there is some issue with character oriented framing. The problem with character oriented framing is um, are 8-bit characters. Okay, so what we do in character here is, okay, let's now let's assume this is our data. So then we will have 8 bits at before, and then we have 8 bits at the receiver, right? This is at the sender, and then at the start and at the end. The flag composes the protocol. Okay. This was popular only when text was exchanged by data link layers. The flag could be selected to be any character not used for text communication. However, we use the problem is this is good when we are using only text communication. But nowadays we also send audios and videos. Then when the receiver return comes in the middle of the data, thinks it has reached the end of the frame. So even when we send any pattern used for the flag could also put a bit a part of the information, right? Now how will what he's saying is, how will the receiver distinguish between these 8 bits of flag at the start, at the end, and then there is data in the between? To fix this, we use something called as byte stuffing. Now in byte stuffing, a special byte is added to the data section of the frame when there is a character with the same pattern. So this is the flag, right? What if this flag and this data both are same? Then we won't know when we are going to send the flag or when we are going to send the data. So what we do is, um, here at the data we do byte stuffing. We add bytes before the data. So in byte stuffing, a special byte is added to the data section of the frame when there is a character with the same pattern. The data section is stored with an extra byte. This byte is usually called the escape character, which has predefined bit pattern. Whenever the receiver encounters the escape character, it removes it from the data and treats the next character as data, not a delimiting flag. The byte stuffing by escape characters allows the presence of. Okay, so yeah, we are going to add bytes to the data to distinguish between data and um, and flags that indicates start and end of frames. Perfect. The character, there is another problem in this. The universal coding system such as Unicode has 16-bit and 32-bit characters that conflict with 8-bit characters. We can see this in general. The tendency is moving. So now there is one more problem that is going to occur over here. Now frame is now when to use bit oriented. Now why was bit orientation, why we saw what was there in byte, right? There was an issue, so we had it at the start. Now in a bit oriented protocol, the data section of a frame is a sequence of bits to be interpreted by the upper layers such as text, graphic, and so on. However, in addition to headers, we still need a delimiter to separate one frame from the other. The Morse protocol uses a special 8-bit flag pattern as a delimiter defined at the end and start, that is 0, 1, 1, 1, 1, 0. This flag can create the same type of problem we saw in byte oriented. That is, if the flag appears in the data, we somehow need to inform the receiver that this is the end of the frame. We do this by stuffing single bit instead of one byte to prevent the pattern from looking like a flag. So bit Stuffing. Why do we uh, no, let's now what is this the problem with byte stuffing? No, then byte versus bit stuffing. When to do what? Okay, so there is something. So remember the flag will be always be this pattern like 0 1 1 1. This is the flag, and this basically indicates the end and start of the data. Now, what if this pattern is present in the data itself? We somehow need to make sure that at the receiver end we are able to distinguish between the flag and between the actual data. For this, there are there are two ways we do. One is byte stuffing, and then the other is bit stuffing. Okay, so now in a bit oriented protocol, the flag can create the same 27 byte oriented protocol. That is, if the flag pattern appears in the data, we need to somehow inform the receiver that this is not the end of the frame. For example, this is 0 1 1 1 0. Now this start we do this by stuffing one single bit instead of one byte. So what you do is the strategy is called a bit stuffing. In bit stuffing, so what the rule says is if a 0 and 5 consecutive 1 bits are encountered, then an extra 0 is added. Now this extra stuffed bit is eventually removed from the data by the receiver. Note that the extra bit is added after 0 followed by 5 ones, regardless of the value of the next bit. This guarantees that the flag sequence does not inadvertently appear in the frame. So This means that if flag like pattern appears in data, it will change to so like if I have a flag, then what I will do, if I have a 0 followed by 5 ones, then I'll stuff it with a 0. Then, after the fifth one, whenever I get uh, if I have a 0, then I have 5 ones, then I intentionally am going to put this 0. So this 0 is not mistaken as a flag by the receiver. The 0 flag is 0 1 1 1 0. Okay. This means that if flag like pattern, the real flag is not stuffed by the sender and recognized by the receiver. So um, now there are two things. So what it's trying to say is when I'm character, so by character oriented approaches, when data is in text, we do byte stuffing, and then so this is okay. This is the flag, right? Now this let's have a shape. Now this and this will determine start. Now we are dealing with variable frame, right? So um, in very we don't know the actual size of the frame, then to indicate the start and end of the data, we add indicator called as flag. The flag is basically an 8-bit pattern added extra, and this is generally it is 0 and 1 2 3 4 5 followed by 7. This is the flag pattern. This is what flag pattern we generally follow. Okay. Let's so now what if this flag pattern comes in data? So then there are two things. One is so is it like depending on the data, if it is text we do byte or bit. So it's basically dependent on data. Then we say why we do text. The text is generally represented like it is going to get encoded in ASCII, right? So in text-based protocols, for example, HTTP or FTP, certain characters like the end or of text control are delimited, such as are often reserved for protocols used. Byte stuffing helps the text is readable in bytes. Byte stuffing helps prevent these control characters from being confused with the data. Okay. So then he's saying, why do we use it's just, yeah. Okay, so then, so how do we determine if we are sending character or bit oriented? How do we determine that? Like, where is the text representation present in the, like, where it will be written? Okay, so remember, this is going to come from top, right? I see. So remember, data link is going to get the data from the network layers, right? So at the network layers, you are going to determine like what data are we sending. If we are sending a character oriented data, then you do byte uh, byte stuffing. Uh, is there a way to move? You know what? Let's. Can I select this region? Does this? Oh, yeah. No, but I need to. Do we have like a magic selectors? No, this is. No, this is not. Uh, mm, can I? Can I move this? I see. Yeah, just give me a minute. Let's get. Let's remove the header from here. Let's get this thing. Let's get this thing also. Let's get this thing done. So then the this is to be. Okay. Let's have this thing here. Now the problem here is, what if the data looks like the flag. So we need to distinguish between data and flag. So then, no, this is. So then, based on the data we are sending, we have two mechanisms. Data we are sending, we have two mechanisms. The first one is if let's change. Let's have another text. If data is character, we do byte stuffing, and then if data is bit, we perform bit stuffing. This is also called as, spelling is wrong, I guess. This has to be data. Okay, so we already did. This is basically this is where we add byte, right? This is byte. Now let's see about bit stuffing. How bit stuffing works. Let's erase this. So the rule says after I get 0 and 5 ones, add a 0. So this is how bit stuffing is. So the moment you get 5 ones in the data, you add a 0 so that the flag pattern and the bit pattern is separated. Okay. Okay, so just to see what we were doing. So the first thing that we were doing is or what? Okay, so the first thing that we saw. The first thing that we saw is what is the data link layer. So the data link layer is basically the layer where we are going to so this layer is something. So the role of this is it's going to do, after this layer we have the physical layer, right? So the role of this layer is going to convert the data signals into electrical signals. Now what device that works? So this is basically the ISP network. Here is what the electrical signals are coming through. This is where we will be having the electrical signals coming in. This is the ISP, right? This is electrical, and then this is the modem. So these are all our devices. Now, these devices we only accept 1 or 0. So what we need to do is we need to convert these electrical signals into bits and then send them to our devices. So this a job is of the modem. It has something called as a, it is a modem because it's a demodulator or a modulator. It's also called as the gateway because the entry to our local network is only accessible because of this modem. If you don't have this modem, then we don't have access to the to other networks, and then there's no point, right? um, okay, so since we are sending the signals through okay, where is the content? Okay, so now there is something called as error detection and correction. Now why we need this is because whenever we are going to send data, now our goal is whatever the sender sends, same thing the receiver should receive. But then what will happen is when data is sent across in the channel, now because of certain problems, for example, if there is any cut or any issue with this transmission, with this physical line, then error may be introduced. Or if the channel is too noisy or it is damaged, then this RF signal will be uh, poor. The poor RF signal indicates that our modem at the receiver end has to perform more amount of work in performing error detection and correction. And hence, when we see on the modem receiver tab, whenever the error rate is high or whenever more amount of error detection and correction is being performed, it usually results in less speeds because more amount of work is done, right? Then there we studied about types of errors. So two single bit error. A single bit error is basically a 1 becomes a 0 or 0 becomes a 1. Only one bit. Burst error is where two or more bits change. Then we call that as burst error. Now our goal is to eliminate this error. We don't want this error to happen. How do we do this? We do this by adding bits. Now detection and correction are two different things. Now detection means is to detect if the error has occurred or not. Correction is basically to check or to correct the errors. Now there are two methods of correction. One is what you kind of do retransmission, and other is you do redundant bits or perform byte or bit stuffing, however you say it. Now framing. Now whenever data is sent, it is not sent as 1 and 0 directly. No, let's so we only this is not this, I don't feel this is right. We only add bits, or what we do is you add redundant bits at the end or at the start, right? Or else is you perform retransmission. Now framing of bits. Now whenever we have data, it's sent in the form of frame. The reason for framing is suppose if this is the receiver and this is the sender and this is the receiver. Now the receiver needs to know when the sender is sending data. If you randomly send 1 and 0, like the receiver won't be able to make sense of it. So what we do, instead of sending single bits, we send frames. Now there are two possible ways. One is you send a fixed size frame. Now whenever fixed size frame is sent, the receiver will know when the packet has, or the frame has completed, because it is fixed size. So we do not need to perform any checking whether the frame has ended or not. It is automatic, right? Now variable size framing. Now when we don't know what the size of the new frame is, so then the other method is variable size. So now the problem here is we don't know the size, so we need to perform some mechanism by which we will be able to tell that we are not send that when the data is being sent, and when uh, like when the size of the data is like complete, right? For that we add something called as frame bits. So what we do is we add 8 bits at the start and 8 bits at the end, and this is basically a flag pattern. Now this indicates the start and end of the data. Now the problem here comes is, what if the data generally the flag pattern is 0 followed by 5 ones and then again a 0. The problem here is, what if my data has this flag pattern? Then at the receiver end I'll come to know, like the receiver will think, this was the start or this was the end, but in actuality that will not be my data, right? So then we need some kind of mechanism, so based to distinguish between the flags and when the data is sent. Now based on what data we are sending, we have two mechanisms. One is we do byte, and one is we do bit. Now when the data is basically a text or a character, we perform byte. By byte stuffing, what we do is we add extra bytes to the data. Now what does this? This increases the size of the data. Okay, but remember, we are not nowadays we are not sending only text, right? We are sending always we are also sending videos and other things as well. So for that we have something called as bit stuffing. Now the rule of the bit stuffing is, whenever we get a 0 followed by 5 ones, just add a 0 to it. Just stuff as a 0. Sorry, just stuff a 0 at the end. So then this will be we will be able to distinguish it between the flag and the actual data that is being received. Just add a 0 at the end. It will so for example, if I have a flag pattern of 0 then followed by 5 ones and then 0, so what we do is, remember the rule says, if I have 0 followed by 5 ones, so if I have 0 followed by 6 ones and then again a 0, if the data is this, and then what we do is we do a 0 followed by, so the solution is, after the fifth one you add a 0. This is called as bit stuffing. That's all for this lecture. Remember, the correct type of data, we will be deciding that at the network layer. There is an header for it which will indicate what type of data we are sending. Have I missed out anything? So remember, we will always we will always give an indication like what type of data is being sent. Mm, yeah, this is done at the higher levels. Yeah, so these are basically at higher levels we'll be defining whether it's character or bit. Okay. That's all for this lecture. Hope you and guys enjoyed this and see you guys in the next one. Till that time, take care. Bye bye.